Come on in. We only got about 1 minute, but if you have any questions, you can go ahead and ask them if you wish. All right, got coming in. So, no questions for those of you already in here? We only got about 5 people in the class so far, 6, 7 people in the class so far. But I wanted to let you guys know, of course, so this will be on the video too. Practice test 4 is available. I did have a errant date on it. It was saying it was due by March 11th, but you guys meet on Mondays and Wednesdays, so it's actually due on March 10th. I've now corrected that. Online test 4 is also posted, and that, of course, is due on March 10th at 11:59 p.m., and that covers chapters 5 and 6. So just letting you know, those are both posted. They have the actual equation sheets built into it, so you don't have to have any kind of equation sheets with you. You have them all there right in the document. Uh, you should be able to, I mean, of course, you're allowed to do open notes and all that good stuff. That's not a big deal. And you're also allowed to do internet searches. But again, you have a little bit of a time constraint. I've actually started leaving it open for 75 minutes now. So hopefully y'all can get it done. Remember, there's a stark difference, though, of course, between the online tests and the face-to-face tests. And if you're leaning too much on looking stuff up and not knowing how to do problems, then you definitely need to fix that because the grades are too highly proportionate based on your face-to-face test, not your online test. They count as a small part. So you got to, I mean, it's good that you want to get as good a grade as possible on that, and I want you to, but at the same time, that's not necessarily going to be enough to help you pass. So you want to make sure you're actually learning the material opposed to just learning how to look up problems. So some of these, of course, are actually available. You can probably find them online. There's a lot of errors on the online solutions too, but still, you probably want to refrain. If you're looking up more than one on a given test, then chances are you're leaning too much on it. So I've now got 10 people in here. Does anyone have any questions before I go ahead and start getting cracking into chapter 7?
Yeah, I think you're probably just going over it, but I think I remember them in lab because I have lab on Thursday nights. Do we have a in-person test t tomorrow night?
No, no. I sent out an email to everybody. Hopefully you will find it somewhere. But no, I've managed to get the face-to-face test moved until after the break. So I'm not sure about classes that meet on Tuesdays or Thursdays, but I do know for a fact the lab that meets on Monday will not have theirs on the 11th when they come back. They're going to have it a week from the 11th, which I think is the 18th. So the Monday labs will actually have theirs on the 18th, which is the Monday, not immediately when they return from break, but the following Monday. As far as I know, Tuesday, Wednesday, Thursday, and Friday labs will all have their exams the week we come back, which is the week of the 10th. If you have a Thursday lab, that would be the 14th. If you have a Wednesday lab, that would be the 13th. So that's when your face-to-face test is. And as far as I'm making it out, it should cover chapters 1 through, for this class, it should be 1 through at least, I would say at least part of chapter 7, if not all of chapter 7. Anything else? All right, well, let's get started into chapter 7. I'm going to go ahead and share my screen with you guys. We're coming up with an entirely new way of solving physics problems in this chapter. This chapter, we're introducing work and energy. That's I think that's even the name of the chapter. But the main thing is we have a quantity that has a everyday layman's word as its name, and that quantity is called work. And in principle, when you do something like that, when you take a quantity that has an existence in real life, everyday life, you want it to bear some resemblance to what the actual physics term is. So what I'm going to do is show you how that particular work does in fact mimic work that we know of in everyday life. So I'm going to do that to motivate an argument for how we're going to define work. So let's imagine for a second that we have a lot like this, and the lot is 50 feet by, and I apologize for using units of feet instead of the SI units, that sort of thing, but it doesn't matter too terribly much. So let's imagine we are mowing this and we have uh, this is a lawn, and we're going to mow it with a 24-inch wide mower. Okay, so what that means is, for instance, we could do one path down here, okay, and then turn around and do another path, and then turn around and do another path. And in fact, it would take 25 trips, let's say north and south. Okay. Now, I would like you to think about that, and let's say we compare that to mowing another lawn. This time the lawn is 100 feet by 100 feet. Okay. We're still using the same mower, and therefore it's still going to take a buttload of trips back and forth, back and forth, back and forth. But in fact, this time it's going to take 50 trips. So which one do you think would require the most trips? One or two? Which one do you think would require I think I said the most trips, but what I meant was, which one do you think would require the most work? Doing the 50-foot wide lawn or the 100-foot wide lawn?
100 foot wide lawn.
Yes. And the reason I'm getting you guys to do that or to answer this question is that I'm wanting you to see that work should be, rather than me using this equal sign, I'm going to say work is directly proportional to the distance traveled, because this right here means the distance traveled would be 25 trips times 100, or 2,500 feet. This one right here would, of course, be 5,000 feet. So we at least see that when the distance goes up, the work goes up. And that's consistent with our everyday definition of work. Because, like I said, you specifically told me that you thought it would take more work to do the 100-foot wide one as opposed to the 50-foot wide one. Does that make sense to everyone? All right, so now I want to consider two different scenarios. So one scenario is I use the mower that is 24 inches wide, but in fact weighs 50 pounds. So I'm going to call this one A. And then I also try a different mower, which is really a new design. And that new design has a 24-inch wide blade as well. But in this case, it weighs like 20 pounds and is equally powerful. And what I mean by that is, technologically speaking, whatever grass you can mow with A, you can also mow with B and go exactly the same speed. So in other words, it's not going to bog down because it's lower power or anything like that. It just happens to be heavier. So which one of these mowers do you think would cut either lawn one or lawn two, just long as you consider it for both of them? Which one do you think would take more work? Mower A or mower B? Yeah, y'all can go ahead and type your
Lower
first.
A?
Yes, mower A would definitely take more work, and that shows that the force should probably be proportional to the force you actually have to apply to the system. That's why I was doing that. What I was saying too, when you answered, by the way, what I was saying as well is, yeah, y'all can go ahead and type in your first and last name into the chat so I can have it as roll. That would be great. That way, in case you forget later, I'll have you on the roll. So we now have two parameters that we know work should depend on. Now, and technically speaking, I haven't told you whether work depends on d to the 1 power or d to the 2 power or d to the 1/2 power or the 2/3 power. All we know is that when d goes up, w goes up. That's because they're on opposite sides of the equal sign, but on the same side of the fraction bar. Both of them are on the numerator, right? Same thing with the force. We don't know if the force should be raised to the first power, the second power, the half power, the 2/3 power, but we do know that work and force are thumbs up, thumbs up. I will tell you that in fact they're just force to the 1 power and distance to the 1 power, and that's what work depends on so far. But I'll also make an argument. I know when I was a kid mowing grass, I would have my mower like this, say, and you'd have the little engine like this, say, and the actual handle was like that. So when I actually started mowing the lawn, what would inevitably happen is the mower would just keep doing its thing or whatever, but inevitably the handle of the mower would go up, and then I would end up pushing with my head like this, uh, and pushing like that. Okay. So what I realized is that in so doing, my body evidently found what it thought was the easiest way to mow it. Specifically, it found that when the force that I applied was parallel to the direction that I was traveling, then it seems like that actually made the work a little easier, or else my body wouldn't have done that. And there's a real good reason to believe that. For instance, if we take, let's say, a box and put it on an incline, on a flat surface like this, okay, we can say, for instance, that the force acting on it would be F, and we could say that that force is in fact 200.0 newtons at 37 degrees, right? We could also say that this force, this block has acting on it a friction force equal to 50.0 newtons. And we could say that the mass of this guy is 20.0 kilograms. So I'm going to show you what happens here. And we can use this as a problem later, but I'm going to go ahead and draw the free body diagram. So the free body diagram would look like this. So here's my x-axis. Here's my y-axis. I have acting on this a force. Oops. Shawnee City just tried to call me again. I have acting on it a force right here at 37 degrees. I also have acting on it a force in the negative x direction. That force, since it's actually parallel to one of the axes, I'm going to actually use a vector that's black to indicate the fact that it's in the negative direction. So this force is F is equal to 50.0 newtons. Okay. Notice the purple one is not along the x-axis or the y-axis, so I'm not going to use any specific colors. But I do know, for instance, that there is a force acting in the upward direction, and that force is the normal force. And then there's another force acting in the y direction. In this case, it's in the negative direction, and that's mg, which equals 196 newtons, because 20 times 9.8 gives you 196. Okay. Now, knowing what I do know about 3, 4, 5 triangles, this is the 4, this is the 3, this is the 5. This is approximately 37. It's really 36.87, but that's pretty darn close. So what I can see is this component right here is pointing in the negative y direction, so I'm going to make it black. And then the other one is pointing in the positive x direction, so I'm going to make it green. Okay, and we know the purple is already 200.0 newtons. So we can see that the green is gotten by taking 200 times the cosine of 37. And of course, you can see that the cosine of 37 from the little blue triangle is obviously 4/5, which is 0.8. So this green force component will actually be 0.8 times 200, or 160.0 newtons. Okay. The black one, on the other hand, will be gotten by 200 times the sine of 37, which you can see is 3/5, which is 0.6. So in that case, we're going to find that it's 0.6 times 200, which gives us 120.0 newtons as the force for that one. Okay. So the reason I'm showing all this is, one, we were lucky in that we were given this F was equal to 50 newtons, because in general, the friction force, at least the kinetic one, is equal to mu kinetic times the normal force, right? So when I go and set up the summation of forces in the y direction equals mass times acceleration in the y direction, what I get is F normal points upwards, so that's going to be positive, minus 196 newtons, minus 120 newtons. And then we're imagining sliding this box across a flat surface. So the y coordinate shouldn't change. Basically, the y coordinate, we could say it's called 0. And I wait a second, it's still 0. And I wait another second, it's still 0. So that tells me the acceleration is actually going to be 0. And what we see happens is that the normal force, which would normally just be the weight, or 196 newtons, in this case, it's 196 newtons plus 120 newtons, which of course is 316. So by having that force not be parallel, but in fact have a downward component, by having that happen, not only have we lost some of the 200 newtons that could be used to push the thing to the right, we've also made the normal force larger. And if the friction depended on the normal force, that means we'd actually make the friction force larger. So it's just a whole bunch of stuff that happens as a result of that. So what we're also going to say is that in some sense, the work done not only depends on the force and the distance, but it also depends on the relative direction, which I'll indicate by theta. Okay, so the relative direction of the force versus the d. That's really what it is. Okay, so using that, and we'll come back and do this example that I've given in a second, or yeah, in a little bit. But right now, what I want to do is introduce a really valuable tool that can help us make sense of work. And that valuable tool is a mathematical tool called the dot product. Okay, so we'll keep this data, we'll make use of it in a little bit, but the main thing is right now I got to continue my discussion of work. So in order to discuss work, I'm going to introduce a quantity called a dot product. Which is also called a scalar product. And I want to stress that because every semester I have a couple of students that will do an actual dot product and put an I hat vector or J hat vector or K hat vector on it. And that's not the way dot products work. They're supposed to be scalar products. But the dot product can be called A dot B. Okay. Now I'm going to give you some information about this dot product. And this dot product, this information I'll give you, gives you two different ways to actually calculate the dot product, at least in Cartesian coordinates. So the dot product, A dot B, is in fact the magnitude of A times the magnitude of B times the cosine of the angle between them. But in order to use this, we really need a picture to go along with it so we can make some sense of what we mean by cosine theta. So let's say this purple vector is vector B, and let's say this blue vector is vector A. Notice they're tail to tail. So I'm going to say tail to tail. And with them tail to tail, that's the angle theta that I'm referring to. So if you take the time to consider moving the vectors so that they're tail to tail, once you get them tail to tail and you find the angle theta, then you can actually calculate the dot product, assuming you know the magnitude of A and the magnitude of B. So I want to put this up here just to remind everybody that this is the magnitude of B, which we clearly don't want to write that way because that's just a lot of work. And this A is the magnitude of A as well. Okay, so that's one way we can calculate it. But in order to calculate it, we need not only the magnitude of A, we need the magnitude of B and the angle theta between them when they're tail to tail. Now, there is another way of calculating it. And if we're talking about Cartesian coordinates where you have an x-axis, a y-axis, and a z-axis, then you have a component that points in the x direction, either positive or negative, a y component that points in the y direction, and a z component that points in the z direction, so on and so forth. Then you can also say that A dot B is the x component of A times the x component of B plus the y component of A times the y component of B plus the z component of A times the z component of B. Okay, so that's a whole nother way of calculating it. Okay. And in fact, that comes in really handy because if you know the components of the vectors, and you don't have to have all three, you should, for dot products to be important at all, you at least need two-dimensional. So you'd at least need one of the vectors to have two components, but they don't have to have three. That just means if they don't have a k component, which is a z direction, then you just put a 0 there, and that's fine too. But if you do have the other components, then you can take a the x component of A, multiply it by the x component of B, take the y component of A, multiply it by the y component of B, and let's assume that the z's are zero. So 0 times 0 gives you 0. Then you just add those two products together, and that will give you the actual dot product. Now, since you have the x component, y component, and x component, y component of A and B both, we also by necessity know the magnitude of A. The magnitude of A, of course, is always, if we're talking about Cartesian coordinates, it's ax squared plus ay squared plus a z squared. And similarly, the B magnitude is bx squared plus by squared plus bz squared. So clearly, if you have enough components where you can do that right-hand side version of the dot product, then you also can compute A and B, the magnitude of A and the magnitude of B. And that, in fact, allows you a way to figure out the angle between two vectors. Now, that might sound like something that's not all that helpful, but to be honest with you, it is actually quite helpful. One of the first things you do when you study a branch of physics called solid state physics is they teach you some of the ways that atoms or molecules get together when they're forming solids. So, for instance, one of the ways that solids form is you could have an atom here, an atom here, an atom here, and an atom here, and then you go back to a slightly further back plane, and then you have these atoms on that layer back there. Okay, that's called a cubic lattice. Okay, well, there's also other ones. You could, for instance, have, I'll make these the front ones, so I'll make them a little bigger. I didn't do much of that in the other one. But what I can do now is I can say this guy and this guy are further back. That's why they look smaller. And you could do like this. But I wanted to show you a slightly different type of lattice. And in this lattice, what we'd have is a body-centered cubic. And of course, it doesn't have to be cubic. You could actually have a body-centered rectangular maybe, and then it'd be a little bit different. But the important thing with this is yet another one. Let me go ahead and show you another one too. We could, for instance, have these atoms on the front row, and then I could have these atoms back here on the back row, hence I'm drawing them smaller. And again, we get what looks like a cube. But in this case, we're going to have some additional atoms. This one's going to be right on the face. This one's going to be on the right face. That one's going to be on the left face. This one's going to be on the top face. This one's going to be on the bottom face. And this one back here is going to be on the back face. This one's called a face-centered cubic. So these are some of the ways that we found that atoms and molecules arrange themselves in solids. And it turns out one of the important things about understanding how they behave is, for instance, what's the angle between this bond and this bond? Or what's the angle between this bond and this bond? Like that. So it turns out once you have the understanding of what the different cubic lattices are, then you could, in principle, render them in 3D using the appropriate size units and stuff like that. Then you take and represent each atom's location with a XYZ, and then you create a vector from, let's say, the bottom left corner, the bottom front left corner, to the middle in the body centered cubic, and then another vector from the bottom left front corner to the top left front corner, and take a dot product of those two, set that equal to the dot product where you have the magnitude of the length of one of them times the magnitude of the length of the other times the cosine of the angle between them, and that allows you to determine that angle phi. You could also do it for the angle theta and so on and so forth. So this is something that comes up over and over again. It also turns out, for instance, that if you wanted a better estimate of how much rain is going to come through let's say a window. So if you imagine a window in 3 dimensions, this would be more like a sunroof. Let's say like a sunroof like this, okay? And if there was rain and the rain was coming down at this angle, then it might not be all that reasonable to say that we can take the amount of rain we get and just multiply it by the area of that window. In fact, maybe the part that's most relevant is if you imagine a single raindrop, it's going to have a velocity that is parallel to the window and then another velocity that's perpendicular to the window hole. So if you actually knew that angle theta right there, you could take the dot product of the rain velocity with that vector that's perpendicular to the window, and it'd give you the part of the rain that's going straight down. So not only is this helpful for figuring out rain going through holes, but it can also give you how bright the sun would be through a particular hole in a wall or a hole in a ceiling. I actually also did another example today in my lecture from something I used to help teach over at Blackwater/Z/Academy. And all that stuff. But it was a little macabre, so I'm not going to put that on the internet. Plus, it's, a little sensitive because it was literally, training Blackwater people for war. And one, there's a lot of good people that work for Blackwater, and they had a lot of bad things happen to some of them. And two, there's a lot of good people in foreign countries that weren't necessarily treated that good by the company. So I don't want to get on either side of that, so I just dropped it. But anyways, whenever you're trying to find a vector, if you need a particular component of it parallel to another vector, the dot product is your guy. Okay, so let me give you an example. Let's imagine, for instance, that we have a particular vector. I'm going to say this vector right here has a magnitude of 50.0 newtons. Okay. And let's say that I'd like to know the component of it parallel to this vector, which, let's say this vector has a magnitude of 200.0 newtons. Okay, so this will be vector B, and this will be vector A. Okay, and I'm going to say this angle right here is 36.87 degrees. Okay. Now, the reason I'm doing all of this is I want you to realize that I can actually make a right triangle out of the vector A, and that right triangle is represented by this red triangle right here. So there's our right angle, right? And if the magnitude of A is 50 newtons, of course, the magnitude of B, that's the 200 newtons. Can someone tell me what the length of that component of A parallel to B is? So I'm asking, what is the magnitude of the component of A parallel to B. And I'll put a vector symbol over it since I'm using words like parallel, stuff like that. So I would like to know, what is the magnitude of the component of A that happens to be parallel to B? I have everything you need there to actually compute it. So can someone tell me what that would be? I will tell you this. There's a name for it that we use in linear algebra, and it's the projection of A onto B. And that projection is technically supposed to be a vector, so I could put a vector symbol over it as well. So can anybody tell me how long this is? Because that's what I'm asking in this question, is how long is that little component of the vector? Anyone? I'm giving y'all a little bit of time to answer. I'm also trying to clean this up a little bit. So can anybody tell me how you might calculate the length of that little guy? It should be a straightforward trig question. That might actually work, Infinity, but I'm thinking that if I'm thinking what you're saying, that could possibly work, but it's a lot more work than what I'm looking for. I'm looking for something simple relating a trig function and the 50 newtons. And actually, yeah, she might even been answering something earlier. I'm not sure. All right. Well, I'm going to go ahead and tell you the magnitude of it now, just the magnitude. I still got to build some stuff to make it into this projection, but the magnitude of the answer would be just A times cosine 36.87, right? Because if you look at this diagram, you could say the sine of 36.87 is equal to opposite over hypotenuse, which would be A perpendicular over 50.0 newtons. And now if you do the cosine of 36.87 degrees, you'd get A parallel to B over 50.0 newtons. So do you see that the answer is just A times cosine 36.87? Does everybody see that? Anybody have any questions on that? So now I want you to look and notice that A times cosine theta actually appears in the dot product. Okay. So I really want it to be A times the cosine theta. So as a guess, I might say it's going to involve A dot B. Of course, the problem with A dot B is not only a dot product, but it's a scalar product, which means it's a operation that takes two vectors and spits out a scalar. So this A dot B is not a vector, and the projection of A onto B is definitely a vector, right? Not only that, A dot B is A times B cosine theta. So it's off by a factor of B, which tells me I need to go ahead and divide by B. Okay. Now the actual magnitude's right, but the problem is the magnitude is right, but it's not a vector. So what I need now is a vector that I can multiply by this scalar a dot b over b, and I need that vector to point in the b direction because I'm really trying to calculate the projection of a onto b, which is a vector that points parallel to b, but is only as long as the component of a parallel to b is. So I've got the component of a parallel to b, but I don't have the actual direction. So what you might hopefully be aware of is if I multiplied this by the b unit vector, then the magnitude of the b unit vector is just the number 1. So that would work. So I could just write b with a hat over top of it, and that's exactly right. It turns out if you want to know any vector, let's say x hat, all you have to do is take 1 over the magnitude of x hat and multiply it by the x vector, which would be basically x sub x over x I hat plus x sub y over x j hat plus x sub z over x k hat. So that's the prescription for making any unit vector that we want. So now all I have to do is replace this with, instead of the b hat vector, I'm going to write a dot b over. Now to make the b hat, I need b, and then I need to divide it by b the magnitude. I've already got one b magnitude down there, so I'm going to make this b squared and put the vector b here. That's the actual formula that you would use, for instance, in linear algebra if you're happen to take that class right now, or if you take it later. Okay. So everybody see how that dot product actually gives us a component parallel to the other vector? That's exclusively what we use a dot product for. I shouldn't say exclusively. We use it for some other things as well, but it's almost always something that you can relate to two vectors, and you're trying to find the component of the vector parallel to the other one. Now, I did this for these two vectors as if I wanted to find the component of A parallel to B, but I could also use it to find the component of B parallel to A, and all I'd have to do in that case is I'm going to change colors here, and I am going to imagine that this A vector might in fact go a little further out, might not have to though, and now I've got a right triangle made out of the B vector. So this quantity right here, which I'm going to make it gray. Okay. So this quantity right here, which actually looks black now that I think of it, or now that I see it on here, that quantity is the component of B parallel to A. And therefore you see it's B times cosine 36.87. So the order doesn't matter. You can think of A dot B as the component of A parallel to B, or you can think of A dot B as the component of B parallel to A. That's basically the beauty of it, is you can use it either way. And if you really just need that part, you might have to do some other stuff like I did here with the projection. So just to round the circle here, I'm going to say that the projection, in this case, it's the projection of B vector onto A vector, is in fact still A dot B, but this time, notice the little vector that's a subscript. That's the one that appears a lot. So in this case, it's going to be A squared times vector A, like that. And that's the formula that you could use if you're wanting to find the projection of B onto A. Any questions on that? All right. So let's say this. Let's say we have a vector. I'm going to draw a vector, and the vector is going to be from here to here. I know this vector, in fact, has a magnitude of 5.0 meters per second. And in fact, I'm going to call that vector A. Okay. And I'm going to write vector A as 3.0 meters per second I hat plus, or actually, no, I want 4.0 seconds, meters per second. So I'm going to call this vector 4.0 meters per second I hat plus 3.0 meters per second J hat. Okay. And let's say, just for argument's sake, that this is our x-axis and that's our y-axis. What I would like to know is, what is this angle theta? I think because of what I've written, you probably can already guess the angle. Can anybody guess what that angle is?
Is it the 345 angle?
Exactly, which is in this case the opposite
30.
angle is the smaller side, so it's, yeah, that's exactly right. It's the 36.87. Okay. So what I'm going to do now is show you how I can use this to figure out what that angle is. Okay. So we know what the angle is. That's the beauty of using this particular problem. But what I'm going to do is draw another vector. And let's say I want this vector to be green. Okay. So I'm going to draw a vector that's actually parallel to the x-axis because I want to know the angle between the vector A and the x-axis. So if I just make up any vector B that is parallel to the x-axis, then this will give it to me. So what I'm going to say is B is 7.0 meters per second I hat. Okay. So what is theta? So that's the question. Now I'm going to say solution. The first thing I'm going to calculate is A dot B. Notice A and B are, in fact, tail to tail. That's the first thing we need to do. So A dot B is going to be, remember the way that I said we could do it. I'm specifically referring to this one because I know the components of the vectors. So I know the x component of A is 4.0. I'll just write it as 4 to save space. I know that the x component of B is 7. So I'm just going to write a 7 there. Then I have to put a plus. Now I got to do the the y component of A, which is clearly 3. And then what's the y component of B?
Zero.
Exactly. So I'll put a 0 there. And then I've got to do the z components, which both are 0 in this case. So I've got that. So I know already that the dot product is 4 times 7, which is 28, right? And then 3 times 0, which is 0, and then 0 times 0, which is 0. So the dot product's 28, right? I also know that the magnitude of A is just 5.0 meters per second. I also know that the magnitude of B is 7.0 meters per second as well. By the way, that's also called just plain A, and that's also called just plain B. So I know that A dot B can also be computed by taking A times B times the cosine of the angle between them, right? So I can now say 28 is equal to 5.0, ignore the units like I did before, times 7.0 times cosine of theta. So I get 28 is equal to 35.0 cosine theta. And from this, I can see that cosine, or excuse me, I should say, let's do it this way. I can say, oops, left off my arrow. Theta is equal to the inverse cosine of 28 over 35. Okay, so you guys go ahead and take your calculator and do cosine inverse of parentheses 28 over 35. And lo and behold, we get 36.87 degrees, which checks. Okay, see how useful that was? Any questions on that? Now, if I wanted to know what is the component of A parallel to B, if I wanted to know that, all I got to do is say A parallel to B is equal to A dot B over B. Remember, we figured that out up there a little bit earlier. I know that A dot B is 28, and I know that the magnitude of B is 7. So guess what? We get 4.0. So you can see now how that dot product comes in handy. Does that make sense to everyone? Anybody have any questions with that? All right, let me separate this a little bit so we can make more sense of it when you're looking at your notes. I know I didn't do a bang up beautiful job, but I can at least separate it where it won't look quite so bad. So all that was that part of the problem. And we've now seen that, one, how you can calculate a vector using the component, or excuse me, calculate a dot product using the components. That's what I did with 4 times 7 plus 3 times 0 plus 0 times 0. And we've also seen how we could calculate it with magnitude of A times magnitude of B times cosine of theta. And we've also seen how we can use it to find a component of a vector parallel to another vector. So does anybody have any questions on that? All right, one other thing I'll show you, and this is kind of nice, it'll come in handy later. If we had a vector, let's make a very simple vector that doesn't necessarily have anything meaningful about it. I'm going to say vector A is equal to 3i hat plus 4j hat plus 1k hat. Okay. And then I'm going to say vector B is going to be equal to, let's do 1 I hat plus 2 J hat plus 3 K hat. So from this, we can figure out that the magnitude of A, which again, I'd never write it that way, I normally write it this way, is just going to be the square root of 9 plus 16 plus 1. Of course, 9 plus 16 would have been nice because that's 25, but now I've got the square root of 26. So the magnitude is the square root of 26. Now 26 is 2 times 13, and 2 is not a perfect square, and 13 is a prime, so there's no really nice way of making that any better, so we'll leave it. I'll also say that B is equal to the square root of 1 plus the square root of 4 plus the square root of 9. Does everybody see how I did that? I skipped a step, and I'm hoping that everybody followed me because it's supposed to be somewhat something you already knew. But if you didn't, definitely let me know. Does everybody see how I got 9, 16, and 1, and 1, 4, and 9? Anybody need help with that? Okay, so 1 plus 4 is 5, plus 9 is 14. So now I get the square root of 14. And the square root of 14 is 2 times 7. So it's the square root of 2 times the square root of 7. Not very helpful again, so I can't do anything with that. But that gives me something. Now, the only reason I wanted to do that is just to make sure you guys knew how to calculate a magnitude of a three-dimensional vector that's in Cartesian coordinates. The part that I wanted to show you is this. I want to calculate A dot B, and I've mentioned that this dot product is what we call an operator. It's a machine. You can sort of think of it as a machine that takes a certain input and only that kind of input and spits out a very specific type of output and only that type of output. In the case of the dot product, it takes in two vectors and spits out a scalar. Okay. So it happens to be what we call a linear operator, which means you can sort of take a sum of a bunch of different vectors and it'll like sort out the scalar parts and the vector parts, and such that you'll have all the scalars like out in front, and then vector dot vector plus all the scalars out in front, vector dot vector, and so on and so forth. So let me show you how that works out. I'm going to say this is 3 I hat plus 4 j hat plus k hat. I'm not going to take the time to write 1 this time, but I will in a second. You'll see. And then this one's going to be I hat plus 2 j hat plus 3 k hat. So what do I mean by carrying this out another way? What I mean is treat this just like a trinomial multiplied by a trinomial. So that's what I'm going to do. I'm going to take this term and let it hit that one. So I'm going to get 3 I hat dotted with I hat. I'm going to now take this guy and let it hit that one. And that's going to say, I'm just putting everything, I'm separating everything by a plus. So now I'm going to do 3 I hat dotted with 2 j hat. Now one more, I'm going to do 3 I hat dotted with 3 k hat. So I'm going to get 3 I hat dotted with 3 k hat. I'm showing more steps than is really necessary here. You'll see my reason in a second, because I'm going to reduce this to something really simple that can help us quite a bit. And by the way, that's supposed to be, yeah, that's good. Okay, so that's the first part. Now the next part is going to be this term has to hit that guy. Then it has to hit that guy. Then it has to hit that guy. So now I'm going to say plus 4j hat dotted with I hat. Again, separated by plus. I can put parentheses around it if I want. 4j hat's going to hit 2j hat. So I'm going to say 4j hat dotted with 2j hat. And now 4j hat's got to hit 3k hat. So again, separated by plus. 4j hat dotted with 3k hat, like that. Now all I have left is the third term. So I'm going to use red this time, and I'm going to say k is going to hit the I. So that's going to be k hat dotted with I hat. In this case, I don't have any scalars in front, so I don't even feel the need to write a parenthesis. Now I'm going to do the k hitting the second term. So again, separated by plus. It's going to be k hat dotted with 2j hat. And then finally, I'm going to let it hit the 3k. So again, it's separated by plus, and I get k hat dotted with 3k hat. Now, it seems like a lot of work here, okay? So, but that's because I'm showing you all the stuff that's happening. When you're done with it, you're never going to write this many steps, okay? So what I'm now going to do is I'm going to take all the scalars and pull them out in front. So for instance, that first term, I have 3i hat times 1i hat. So I'm just going to write this as 3 times 1, and then I hat dot I hat. This is what I mean by the dot product being a linear operator. It took the scalars and just pushed them out in front, and then it let the vector operation act just between the vectors, and you can ignore everything else. Now I'm going to do the next one. I'm going to get 3 times 2 times I hat dot j hat. Now I'm going to do the next one, which is 3 times I hat dot k hat plus 4 times 1 times j hat dot I hat. Just stick with me. It's a longer process than it really is. I just want you to see it once and for all. Now I'm going to do 4 times 2 times j hat dot j hat. And then I'm going to do 4 times 3 times j hat dot k hat. And now I'm going to do 1 times k hat dot I hat plus 1 times 2 times k hat dot j hat plus 1 times 3 times k hat dot k hat. And remember our rule, A dot B is equal to A times B times the cosine of the angle between them, because this is going to come in really handy in a second. 3 times 1 is just 3, but I hat dot I hat is just 1 times the cosine of 0. Does everybody know why I have cosine of 0 there? Can anybody tell me why I have the cosine of 0 there when I'm trying to compute I hat dot I hat? Remember theta in the A dot B is equal to AB cosine theta. Theta is supposed to be the angle between the vectors when they're tail to tail. These two vectors, I hat and I hat, are identical. So the angle between them is 0. And of course, the cosine of 0 is 1. So we see all of this, whoa, all of this is just 1. When we do I hat dot j hat, we're going to get 1 times the cosine of 90 degrees. Everybody understand why that's 90 degrees? Can someone please word that for me? This thing on? So I hat and j hat, I hat's parallel to the x-axis, j hat's parallel to the y-axis. The angle between them is 90 degrees. So cosine of 90 is actually equal to 0. So that's why I had written 0 a second ago. Of course, the same thing happens here. J dot I is 0. J dot j is 1. J dot k is 0. K dot I is 0. K dot j is 0. K dot k is 1. So ultimately, all I'm getting is 3 plus 0 plus 0 plus 0. Now I'm up to the 4 times 2, so I'll say plus 8 plus 0. That's the 4 times 3. just trying to show you where I'm getting all this. So this 0 is 4 times 3. Then I have k dot I, which is the 1 times 1, but the k dot I is 0, so that's a 0. Then I have 1 times 2 times k dot j, but that's 0. And then I have 1 times 3, which is just 3 times 1, and that's it. So you can now see that I have 3 plus 8, which is 11, plus 3 is 14. Okay, so that's another way you can do the dot product. Notice I wrote out all that stuff, but if you were actually doing this, you would write 3 times, or 3 I hat dotted with I hat, and you would just write that down as 3. I hat dot I hat's 1. You wouldn't even write that, so you just write 3. And then when you did 3 I hat times 2 j hat, you'd know that's 0, so you wouldn't even write that one down. When you did 3 I hat 3 k hat, you knew that was 0, so you'd skip that one. So you'd literally just drop right down to this next to the last step and get exactly the right answer. So that's A dot B. Okay. So see how you can force yourself to actually push all the magnitudes of the vectors to the left, and then just have like a I hat dot I hat, or I hat dot j hat, or j hat dot k hat. That's the other way that I was showing you. Okay. Any questions on that method of calculating a dot product? Okay. Well, now that we have that, I've given you more than enough about dot products. What I want to do now is take this little part right here at the bottom of this page, and I'm going to calculate this. Oops, there I go again. It keeps erasing. Stop erasing. Copy. Okay. So I'm going to pull this over to here and say paste. And now I'm going to move it right here. And that seems to be pretty good. Okay. So if we imagine that we actually were moving this this box here, if we were actually going to move it a huge distance, let's say 100.0 meters, like that, okay, then I would argue, because of our definition of work, we found that work is actually going to be F dot D, as long as F and D are constant vectors. That means their angle's not going to change, their magnitude's not going to change, or anything like that. So this is sort of a simple version of the work formula that I just sort of derived for you. I'm going to show you a more detailed one for the case where the force and the distance vector could actually change. But right now, all I need to do is use this one. So I'm going to say work for this case is actually equal to, well, the force we applied was 200 newtons. So I'm just going to blindly apply the formula and say 200.0 newtons, because I'm using the idea that A dot B is equal to A times B times the cosine of theta. And again, remember your diagram. And it wouldn't matter which one I drew to be A and which one I drew to be B, as long as they're tail to tail like this, we're good to go. And I'm sorry that B turned out so badly. Okay, so that's the formula I'm using. So I'm going to say 200 newtons. And now I'm going to take the displacement vector, which is 100.0 meters. And now I've got to take the cosine of the angle between them. Well, I think you can see that the D vector, which I'll draw right here, And I'm putting that little break in it just to show you that obviously it's a lot longer than this is suggesting. But you can see now if I pulled this, if I pulled the force vector through, it would be right along here. And you'd see that this angle and this angle are in fact what we would call vertical angles, and therefore by necessity have to be equal. So now I've done the equivalent of expressing the two vectors as if they're tail to tail. So I can just blindly write in 37 degrees here. So this is a way I can do it. I'm going to say 200 times 100 times cosine 37. And this gives me Nelly. This gives me 1.60. Actually, I can do it better than that. That gives, dang it, stop this. Ugh. It gives me 1.597 times 10 to the fourth. And the unit is a Newton times a meter, which is going to be called a joule. So I'll put this here. The dimension or unit of work is equal to the dimension or unit of force times the dimension or unit of displacement times the dimension or unit of cosine theta. That, of course, has no units and no dimensions. So this one's just going to be newtons times meters. And what I say is 1 Newton meter is defined to be 1 joule. Named after James Prescott Joule, who was a beer maker, a cannon maker, and a guy that worked on what we now call thermodynamics. And he made beer, and the beer still exists in Great Britain. It's called Jowls, but that's the same dude. Okay. I will give you also, physically speaking, the amount of energy that 1 joule is about the amount of energy it takes to take a nice, good, red, delicious apple from the grocery store. If it's laying on the floor, you pick it up and put it on a dining room or a kitchen table, not a bar, but up to a table height. That work required to lift that normal size red, delicious apple up from the floor to the top of a kitchen table, that's 1 joule. Okay, that'll be a nice little perspective, because later we'll learn about a 100-watt light bulb, which is basically enough energy that it could lift 100 apples from the floor to the table every second. That's what a watt is. So if you start thinking that way, you say, oh, well, actually electricity is kind of cheap, because, you know, how much would it cost you to pay somebody to keep moving 100 apples from the floor to the table every second for every second that you have the light running? So there's one way of doing it. It's just the force times D times cosine of the angle between them. Another way you could do it is you could say work is equal to the force component that's actually parallel to the distance. Okay. So we actually already worked that out. If you look up above, we can see that the component of the force that's parallel to the distance is the 160 newtons. So in this case, I'd write 160.0 newtons times 100.0 meters. And I think you can see at least that when you round this one, it comes out to be about the same thing. So I get 1.60 times 10 to the fourth joules again. So we can see that both of them check out. Does that make sense? Any questions on that? Okay, so now I'm going to generalize it a little bit so you actually know what work is. If we happen to have a scenario, let's say like this, where I have a y-axis and an x-axis, and I'm actually going to follow a little path, say like this, in doing the work. And let's say right here, the force is that direction. There, it's that direction. This one, it's this 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 direction. And this one, it is this direction. Then you also have, of course, the DL would be that little guy, and that little guy, and that little guy, and that little guy. Okay. If you had that, what you could do is divide that little path up into a bunch of little short intervals. And then if you made it short enough, then the actual angle between the purple force and the vector, the little red vector that represents a tangent vector to that curve, that angle's not going to change much. The magnitude of F's not going to change much. The magnitude of the tangent vector is not going to change much, nor are the actual directions going to change much. So you can actually do it for just this guy, and then another one for this guy, and another one for this guy, and another one for this guy, and another one for this, and then add them all up, and you would get a really good approximation. So in that case, the work would be the summation from I equals 1 to n of F sub I dotted with DL sub I for all of those. Okay. Well, if you find that it changes too rapidly to just do that by hand, then you might have to break it up into 10,000 or 100,000 or 2 million individual intervals, in which case this becomes work is equal to the integral of F dotted with DL. Now, your book tells you this is called a line or a path integral. Whoa. Now, if you look in your calculus text, assuming you still have it, you will find in the very near the end of it that there's path integrals. Some books call them path integrals. Some books call them line integrals. Some books call them both. You'll have to look for both names. But in your calculus book, you will find things about path integrals or line integrals. You'll find surface integrals and volume integrals. Those are hardly ever gotten to in a Calc 3 course. So, as luck would have it, when you're in a physical science like physics or engineering, you're often going to learn your mathematics from your physics or your engineering instructor, and that's what's happening here. The big thing is your book does tell you that this is a line integral, and it tells you that F could be written F sub x I hat plus F sub y j hat plus F sub z k hat, and then dl would be written dx I hat plus dy j hat plus dz k hat. And he's technically correct that can be done, but often you don't have to. So for instance, if you actually wanted to integrate along the path y equals x squared, to make this path integral work, if the function f, that is a vector function f, if it has both y and x in it, then you can replace every y you see with x squared, and you've done what you're obligated to do in the path integral process for assigning this integral to be conducted along the path. You've at least done what you were supposed to do with regards to the force. What you then have to do is maybe replace this dy in the dl, just replace that with 2x dx. Okay. And you can leave the other one as dx I hat, and then you'd have dx I hat plus 2x dx y hat. Now you've evaluated both f and dl on the path, and all you've got left is to dictate from what variable to what variable. So the big thing with this, and here's a sentence I'm going to say, and you guys need to figure out a way to write it down, because when you do a line integral, you either have to let DL point in the direction you're integrating. And if you do that, your range of integration goes from small coordinate to large coordinate. In other words, the bottom symbol below the integral will be the lower of the x, y, or z, and the top above the integral will be the higher of the x, y, z, whereas dl will just point the direction you're going. So it could be like in the negative dx I hat direction. So that's one choice. Write that down as a sentence. You've used the DL to show the direction. Then you used increasing coordinate for the range of integration. That's one. The other option is you let the range of integration show which direction you're going. So you'd start the bottom at the initial position and the top above the integral. That range would be the end position. And then your DL just points in the positive coordinate direction. So that would be automatically just DX I hat, say, if you're going in the X direction, if you're going along the X axis in either direction. So that's usually the part that stumps people is you'll inadvertently take the range of integration and set that from 5 to -3. And then you'll also put DL is equal to negative DX I hat. So what you did is you counted the direction twice and you're going to be off by a negative. So that's the big trick of doing this. What I will tell you though is your book does one where it's taking a backpack, putting it on a backpack on a hiker's back, and then he's going to walk up a slope of angle theta whose height is 10 meters. Okay. And then they ask you to calculate the work done by the force the hiker's applying, and then the work done by the force gravity's applying, which is the mg. And you're doing it in such a way that it doesn't accelerate. So the normal force, the hiking force, is exactly equal to the mg. So they're equal in magnitude, but opposite in direction. But since you're not accelerating it, the force points up and it'll be carried up the incline like this. So all that matters really is the component of the displacement that is parallel to the force. So really all you need is the 10-meter height multiplied by the 196 Newton force, if it's a 20 kilogram pack, for instance, and that would give you the work done by the force of the hiker. In the case of the force of gravity, that force is pointing straight down, but the component of it parallel is pointing straight up. So you end up getting the 196 times the 10 meters times the cosine of 180, which is -1. So you'd get a negative 196 times 10. So that's basically it. I wanted to spend this time making sure you understand exactly what work is, exactly how we motivated what it's defined to be, and giving you examples to show you how it works. I will do more examples when we get back, of course, but that's it. We're done. You guys are free to go. I hope you have a great spring break. Do not forget your online test that's due on March 10th before you come back. Don't miss that. Get that done. Then also when you come back on the 13th, you will have the face-to-face exam, and it will have some part of this chapter 7 in it. Okay. That's you've got all this time to work on chapter 7, even though chapter 7 homework's not going to be due until the Sunday you come back. But I
Can
could,
ask-
yes, go ahead.
Chapter 7 looks like it's due tomorrow.
Yeah, I got to change that.
Okay,
So it'll be changed like in 20 minutes, probably. Okay. So yeah, I'm going to go ahead and probably it'll be the low hanging fruit of chapter 7. So I'm not going to ask you really hard stuff. You'll have a day to ask me about it, but you should at least be able to calculate the work done by something. You're not going to have to do the work energy theorem, which is in there. You might have to use work is equal to 1/2 kx squared because that's a result that they just give you in the textbook. But other than that, you just got to do this kind of stuff in dot product. So a dot product will be a fair game. You'll see when I make the practice test up, you'll see what kind of problems you have. And that'll be available sometime tonight or dead latest first thing tomorrow. Don't forget to chat me your first and last name if you haven't already, but you guys are free to go, and I'm waiting for the last person to leave before I do.
thank you.
You're welcome.
Thank you. Good night.
Good night. There's plenty of examples, by the way, on my YouTube channel, as well as in the Canvas modules for this week and last.
Professor.
Yes.
So is the all the practice for like the end of chapter practice, like chapter one practice, chapter three practice,
Right.
not like the test practice. Are
Mhm.
those also like um because the syllabus say like if you like finish those, so you got the test practice
Right.
and those chapter practice, and
Right.
the syllabus say something about like getting like bonus point for like doing the practice. Is
Yeah,
that like
it's just the
talking about the
practice
test?
test.
Or
Yeah, it's
just the
just the
test, not
practice test, not the chapter tests. What the chapter tests are for is like you'll see a practice test, like practice test 4 is chapters 5 and 6, but in reality, it's 1 through 6. If you find that you got a weakness in chapter 5, why waste your time doing 1, 2, 3, and 6 and 4? So that's why I put the chapter practice there. You don't get any extra credit for it. I can see that you're doing them, but I really can't tell any details how you're doing, how much you're doing. So the practice tests do count for you as extra credit, but the chapter practice is just for you to have extra practice for a given chapter and no extra,
oh, okay, so it doesn't. Okay,
right?
no, I thought it's like the because you got both the the test and then practice test, and so I was kind of confused.
Yeah,
All right.
yeah, that's all it's for. Just if you want to focus on one particular chapter, you can do that over and over again. And you really all you want to do is you want to make sure every practice test you get as high a score as you can at least once. Ideally, it'd be 100 because then you're going to get 5 points added to your course grade at the end of the semester if you got 100 on every one of them.
Got you. All
Okay.
right.
All
Okay.
right. Have a good one.
All right. You too. So
Jonathan, you have any questions? Okay, I don't think he's here and I don't see him typing anything, so I will go on. Bye, everybody. Remember, there's plenty of examples of me calculating work on my YouTube channel. You can just do Google searches for the word work. Our Google searches for the word line integral, or Google searches for the word dot product. Any of those are all come in handy. And also, if you look in our Canvas for the week in which we cover chapter 7, you'll see specific examples that I posted there. A lot of them are full lectures, so you really don't want to go through the whole thing. But anyways, that's it. Have a good one. Bye, everybody.